All right, last one. Means I can go on for a couple hours, right? No one's after me. Well, anyways, it's a pleasure being here. I'd like to thank the organizer of the workshop for inviting us. My name is Bruce Davis, and I'm with a company called Rocore, based in Louisville, Colorado. And today I'd like to talk to you about some work we're doing in conjunction with JPL. In fact, we're under contract with JPL to help develop an external occulter for a planet-finding mission. So before I get into the details of the occulter itself, I just wanted to give you an overview of what we do at Rocore, who we are. We're a company based out of Louisville, Colorado, which is just outside of Boulder. And we have about 10 people working full-time in our group. About 6 of them are engineers and the rest are support. And our main mission is to reduce asset cost of spacecraft systems. And to do that, and we do that by making them more elegant. So we're taking new technologies and we're incorporating them into current designs, current systems that have been flown for years, and trying to make them very simple. We also are developing new systems as well, which I'll show in the next slide or so. But one of the approaches to doing this and using new technologies is using high-strain composites. And a high-strain composite is a material that is going to deform a significant amount during its normal operations. And I'll give you some examples of some structures we're working on in that field coming up. We have several contracts going on. We have probably about a half a dozen at Rocore currently. The JPL Occulter that we're working on is one of our bigger ones, as well as some support we're doing for DARPA Phoenix, where we're working on with a company called NovaWorks that does we're building a boom deployer for their aggregate spacecraft. And then I'll also mention that we've compiled a team of some really distinguished engineers who've worked on a whole series of complicated spacecraft systems, who have a very deep background in analysis. Here's some examples of some of those projects that our principals have worked on in the past. I'll point out specifically the AstroMesh design was led in part by one of our engineers, and the occulter has some relevance there. So before I get into the occulter details, I'll just go over some of the products that we sell and kind of give you an idea of what exactly a high-strain composite is. So I brought a couple of them with me. This is just a slit tube. Otherwise, it's known as a stem. It's kind of like a tape measure that you may buy at a hardware store, where you deploy it out and it's rigid, and then you can fold it and you can actually coil it up. And these coilables is a very efficient packaging type structure, so they're used, and they've actually been used since the very beginning of the space program. Our unique aspect is that we're building them out of composites, so we can take this and we can really cinch it down to just an incredible bending radius, and there's no deformation. You can also backbend them to quite to the same scale, and it's just going to bounce right back. It's all about using the proper materials, proper matrix, the epoxy resin that holds it all together, that makes that magic happen. Another nice trait is that if you look in the upper left corner, that's a slit tube that's bistable, which means that it has multiple configurations in which it's stable. So as a matter of fact, we're not actually touching the stem in during any one of those configurations, because you just you open it up, you take your hands off, and it stays. So as a result, when you build a deployer for, let's say, a CubeSat mission, or a more complex, a larger, say a JWST, which has metallic stems, you don't have to have all those complex rollers and constraints inside the deployer to control that strain energy that's stored. In these materials, the strain energy can be 0 during the entire deployment. In the upper right corner, another benefit is you can embed conductors inside the composite. So this is actually a boom that we're developing for DARPA Phoenix, and we actually have conductors inside the boom itself to supply power to the distal end of the boom. And that eliminates the need for a wiring harness and things like that. Another feature is when using composites, you can control the coefficient of thermal expansion. You can make it near 0. You can tailor it to be negative or positive based on your needs. In the bottom left corner, it's a product we're developing right now. It's called the Rock Truss. And I'll actually ask the tech to click that link over there. It's kind of a cool example of how you can take just a single composite slit tube like this and add hierarchy, and you actually form a full truss. So here's a YouTube video of us in our lab. Hopefully it loads here. And if not, then you can take a look at the pictures. But it's a nice example of just the flexibility that you can have, and how these are really building blocks for more complex systems. It's not going to work Let's see here. There we go. Perfect. Thank you.
All right.
There's my colleague. I go, and then you have a full truss. So even though that these composite pieces right here don't have a big footprint, you can spread them out over a larger footprint, and man, you have one heck of a structure. In the bottom right corner, this is something called a seam lock. We're currently developing this. It's a way to lock out the torsional rigidity of a slit tube. That's one of the oh, there may be a YouTube following that. One of the problems with slit tubes is that they don't have torsional rigidity because they have a slit running down the length of the tube. So this is one method that we've designed and developed a preliminary version of that actually reduces the torsion by a factor of 4. So these are some examples. These are all slit tube examples, but as we'll see with the occulter, there's many other types of high-strain materials and composites that we're going to be using. So I'll go on to the next slide, which is just one final slide showing, when you're ready. Oh, I'm sorry, I got this. Thank you. Wonderful. So just an overview of the top things that we do. We do system design, mechanical design of systems. We do composite fabrication, and then we do system development. And in the bottom, we do a lot of our composite fabrication in-house. However, that's more for prototypes, and when we have a more large production scale or flight scale parts that need to be made, then we farm those out. So let's see if I can try this, so I can get this. Perfect. All right, so going into details of why I'm here today, I want to talk to you about the star shade that is being done at JPL. And just for completeness, I know you guys are all experts in this room, but an occulter is a shade used in a telescope to block the view of a bright object in order to allow an observation of a fainter one. And we like to, when doing outreach, we tell kids it's like putting your hand in front of in front of the sun to catch a baseball. You block out all the harsh light in your eyes, and you can suddenly see that ball. And we're going to do the same thing with a star to try to find the planets. So JPL has proposed doing this with a planet, and right now the task is to do a pre-phase A, so a very early study to close some key technologies and to identify what technologies need to be further developed in order to make this a reality. And then here you can see that there's just a graphic showing that exact same phenomenon where you have this flower-shaped petal that blocks the starlight, so that way the satellite, the telescope, can see the planet. So this occulter is very large. It's 34 meters tip to tip, and it needs to fit inside a standard fairing of a launch vehicle. So how do you do that? And that's a tough question. JPL has developed a structural concept for the entire deployed system, as well as a mechanism concept for how the system will be stowed. And probably the best way to explain how that works is to look at it, go through it backwards. So if you start in the bottom right corner, you'll see that's the deployed system. You have the ring truss with 28 petals around it. And what you do is you contract that ring truss, and you fold it up towards the center hub of the structure. And the petals, which are attached to the edge, pentagraph, and then they, in the upper right corner, they become vertical. So that work has been done at JPL and creating that ring truss and the hub structure and certain aspects of attaching those petals to that structure. Now where ROCOR comes in is how do you take, in the upper right corner, how do you go from the upper right to the upper left? How do you furl those petals around the hub and secure them for launch? Now keep in mind that these are optical petals, meaning that they have very high precision. They are very susceptible to damage if you don't treat them the right way, then there can be problems. So how do you characterize what susceptibility that they have, and how exactly are you going to go from the left to right in a controlled form? Whoops, I went one too far. So our objective with JPL is to retire risk by developing a flight occulter system. And our approach, I'll let you, it's kind of detailed, but I'll let you read through that on your own. Our approach really is twofold. One is to do a rigorous analysis of the stowed and deployed configured occulter, as well as do initial testing inside our own facility to mitigate some of these, first of all, to identify some of these issues, to mitigate them, and then eventually to write requirements for a further follow-on study. And then before the next couple slides are going to talk through some of the key areas that were contributing to this design and development. But before I go there, I'll just point out some of the geometry of this occulter, just so you guys are more familiar with the structure itself. Around the perimeter, you see the ring truss, which is 20 meters in diameter. And this truss at a half scale has been designed by JPL, and they did a full assembly this summer. You can see pictures of there's some cool stuff online. There's some YouTube videos you can see of that system deploying. Around the edge are 28 petals. They're each 7 meters in length. They have a spire or a tip on the ends, which come to a fairly tight point. Around the perimeter of the petals are it's kind of like a razor edge, sharp edge, in order for the light to diffract around it. Let's see here. Connecting the ring truss to the hub is a series of spokes. These are composite, basically wire that connects those components together, and there's 112 of those. We have the blanket shield, which is kind of another area within the system that has to be considered. The blanket is a very large system in the sense that it covers the entire footprint of the occulter, and because for reasons of concerning debris or impacts from micrometeoroids, it's actually fairly thick. That way you have multiple layers to prevent any light from permeating through. So it's about 1 inch thick of foam throughout the whole system, which needs to be packaged in, and it also needs to be considered when you do furl the petals. And then in the bottom right corner, just as a reminder, that's the stowed system to scale, so you can compare the deployed versus stowed, and just seeing how much of a deployment spectacular event this is to go from one to the other. Let's see here. All right, so I'm probably going to take the next 10 slides or so and just highlight some of the key things that ROCOR is doing under contract with JPL. The first one is designing the backbone of the petal itself. The petal is going to be furled around the hub, so it's going to be bent, and as a result, we need to control and, first of all, understand the strain in that system, and then design the best profile along the entire length of the petal. You can see there's a backbone in there, and we're determining, they're going to be one backbone, multiple backbones, is that going to be tapered? So we're doing that analysis now. In addition, there's a pop-up rib that rigidizes the petal once it's deployed. And we're using a high-strain composite mechanism to actually, so they'll passively pop out, but then we need to connect the top of those ribs to the truss structure itself, the ring truss. And so we're using a high-strain composite to do that. And again, characterizing and understanding exactly how those edges, those optical edges, are going to perform during as we go from a furled state to a deployed state, how those are going to wear down, things like that. So moving on. Another surprisingly challenging task is to actually model the system geometrically in the furled state. So that's what we're showing here, is we take the petal and we're furling it around this arc, and then we're preloading that petal against the perimeter of that circle. So as you tighten that preload down, and first of all, what is the preload supposed to be? That's another open question that we're looking through right now. As you preload the petals around that structure, they want to contract. And so nominally they'd follow a spiral around because they have to furl with the adjacent petals. But as you tighten that preload down, then they're going to shear with respect to each other. And there's as I mentioned before, there's all that foam, so there's going to be compression happening where the load's being transferred as a result of that, and as a result of where the loads are being transferred, what does the shape look like? On top of that, there's only so many places we can physically tie down the petals. You can basically only attach them at the root of the next petal all the way around. So it's not necessarily a perfect spiral. So we've actually taken a lot of time just trying to specifically characterize how this thing's going to look in the undeployed state. Let's see here. Oh, a little bit of delay there. Got it. All right. So as I mentioned before, the accurate modeling is critical. In addition, one of the reasons is we're trying to model the strain energy of the system, and it's a strain energy that deploys the petal. So it's really important to make sure that, A, we have enough stored strain energy in the system to deploy the system, but we don't want excess strain energy, because then it's going to be harder to control that as the events occur. All right. So on the left side here is our current model from a CAD standpoint of the system, and on the right is the stowed model finite element analysis that we're performing. In this case, our biggest concern, or not concern, but our biggest concentration right now is to understand how the petals are going to be launch restrained during launch, and how are the petals itself going to interfere with or interact with each other in terms of how are they going to vibrate, how are they going to be preloaded against each other and against the ring itself, the truss or the preload positions around the center. So what we've come up with in conjunction with JPL is a series of connection points. Let me look over here, it's more clear. Connection points to understand and identify how those petals come together, and to identify the different ways in which the system can be preloaded. So one method was, do we have an external belt that contracts radially around the outside that we unwind during a deployment scheme, or do we have a series of connection points on the inside that release one at a time, which would involve a significant number of release devices. This just give you a taste of some of the configurations that we've been doing our structural analysis with. You can see here's a few pictures of the mode shapes of the system, and I have two different ones in here. One in which the edges of the petals are deflecting, and toward the center you can see, on the right you can see the center is deflecting a lot. So if there's anything to take away from what we're doing when it comes to an analysis standpoint, is that we are looking at the system in multiple configurations in which you can restrain it from the center with an outside band, or restrain it from the center on the inside, and to understand exactly how these petals are going to react during launch and then during initial on-orbit transfers and things like that. In addition, there's a lot of effort to characterize those blankets and how that foam interaction from one petal to another is actually going to transfer loads and probably even more importantly, induce damping within the system, which would have a dramatic effect on the natural frequency. I'll get into a discussion on exactly how is this thing going to be deployed. And we've been working with JPL for about 2 years now, coming up with different concepts, both a controlled type of deployment and then a less controlled type of deployment where there'd be some dynamic motion. And just to get an idea, we did an early study where we did a dynamic model, which we basically take a single petal by itself, and then just release it and see what would happen. And we found that there was a fairly large amount of velocity at the tip, and it was also what you could probably consider a level of chaos within the tip, in which once you have a whole series of petals interacting with each other, because imagine if you can't release one petal because they're all furled together, but imagine releasing multiple petals at the same time and the tips are all moving. So if you have one hinge point between the petal and the ring truss, if that has a little bit more damping, then you're going to get a non-symmetric deployment, and then the tips are going to interact with each other. And as I said before, they're optical surfaces. There's a lot of concern there. So because of this initial study, the baseline approach has evolved to be a controlled deployment, but there's various types of controlled deployments. One is that one that releases the tips of the petal sequentially around the ring, which is one direction that we're pursuing, and another one which we have a band that completely locks in the exterior of the system and very slowly and with a lot of control releases the segments of the petal part by part. Let's see here. I think I have 2 more slides. Oh, no, I'm sorry. I have to talk about some of the work we're doing actually at ROCOR itself. So we have several petals that were fabricated at our facility now. We have a full-scale truss structure that we've built. You can see here, as well as, so we have this structure here that's circular that represents the diameter of the hub itself. We can see we have a petal on there that wraps around the hub, and then we have a series of, only one show, but we have a series of offloaders that allow us to reduce the effects of gravity on the system. So you can take a look at this concept, and then I keep pressing the button. Okay, then here's our facility itself. You can see these petals. We have 3 of them, and we've been doing a series of tests to validate our models, but also to identify upcoming issues that need to be resolved, such as impact from one to another. So this has been a lot of fun to work with. These petals are enormous. This is only a half-scale petal on a full-scale hub, so it's amazing. We're going to be fabricating larger petals soon to get to wrap all the way around. They go about 120, I think 270 degrees around the whole system, which is a very large deployable structure to be working with in a lab. And then here's some other pictures of some of the interfaces that we're starting to work on. We have a design for a snubber stack. And as I mentioned before, snubbers are the kinematic mounts that hold one petal with respect to another petal. That way they can be restrained during launch. You can see on the left side is some of the CAD coming from the vertical, looking down straight, and there's a lot of foam in there, which is why you don't see any gapping between them. But yeah, we have that green cylinder that represents the mechanism we're developing to release these petals part by part. All right, let's see. I can see better over here. So the other thing that we're doing outside of the high-strength composites is we're actually working on the spokes themselves, which are the wires that connect the ring truss to the hub. JPL needed a group that could design a system that had a very linear strain with respect to a low loading. And we took on that challenge, and we developed a preliminary demo spoke, as we called it, that was metallic this summer for their half-scale truss. And we're closing in on some funding that will develop a full composite system for a flight demo that would be performed, well, not a flight demo, but a full demo system that would be formed in about 1.5 years to 2 years. Oops. So in closing, I'll just go over, just give you a roadmap of where we are at, and some of this is kind of focused on our funding and where that's come from, and can give you an idea for where we're going. So our original contact with JPL started off with a phase 1 SBIR, and that initiated some of the first concepts for how we would furl and unfurl the petals. And that went well enough that we received a phase 2, and that was enabled us to build our hardware and start really getting into the details of this stowed analysis and that finite element analysis system. We're getting ramped up. We're going to be working with JPL in the near future to build a half-scale unit, a half-scale system that is complete in its entirety. So I believe on that previous slide, I'll just go back to that previous slide. I didn't mention that. There was a picture of this truss. So you can see that ring and that center hub is all performed at JPL. It was a phenomenal work of engineering that they did there. And then after it, part of that deployment was contained 4 petals, which didn't have any furling capability. They were just kind of rigidly attached. So when I mentioned that we're going to be working with a half-scale system, we're going to essentially take this ring truss and we're going to do full furling with it, is on the game, as the current game plan. And then, as I mentioned before, we worked on, did some initial work with JPL on the metallic spokes, and we're getting excited to ramp up with some composite spokes that we have some funding things in the works to see if we can start that fairly soon in the next couple months or so. So with that, I went through it pretty quickly, but I just wanted to give you a taste of what we're doing at ROCOR. We're really excited to be working with JPL, and as well as this community being here and learning what you guys are doing. It's been a pleasure. So if there's any questions, I'll take them now.
Can you speak a little bit about how you're getting the near zero CTE? Is this purely a materials approach?
Yes. So there's you can actually acquire a lot of carbon fiber materials have a negative CTE, and then you can actually offset that with other materials that have a positive. On top of that, there's a level of influence that the resin itself has on the structure, because that usually has a fairly high positive coefficient of thermal expansion. So it's really a matter of just playing with the properties and playing with the curing of the composite too, and testing to get that. But it's been fairly well known within high-end composite companies that they can perform near-zero CTE structures. So, go ahead.
So that was the first time that I've seen a dynamic model of the unfurling of the pedal. I'm not really surprised it's chaotic looking. I was wondering if you actually accounted for in that model that the hub isn't itself inertially fixed. Because something I've always been a little worried about is, as you unfurl, is that going to destabilize the spacecraft in any way?
Yeah, that's a great question, and I'll have to put out a disclaimer that I didn't do that model myself, but and I try not to use the word chaotic because that has certain implications. But the reality is it's an extremely complex system, and there's so many factors that go into play, especially the one that you brought up that I didn't, that it's free floating. So there could be some effects there, and you have 28 pedals, 28 independent systems. Surely, and tips that are extremely flexible. There's surely going to be some contact that's not characterizable up there, and there's no way to test it on the ground either. Because so thanks for your comments. I hope I answered it in its fullness. But
yeah,
thank you. Go ahead.
What's the longest boom we can make out of this?
What's the longest boom we can make? That's a good question. It's as long as our oven is in-house, but we can find vendors without difficulty to fabricate a boom that's very long. I know that I bet someone in here knows how long the booms are on. Actually, I'm not sure if JVST has composite or not, but come to us and we'll let you know. I don't know offhand exactly what the longest boom that I've seen in literature, but I know that. Excuse me? We've done them over 100 feet. Done them over 100 feet, yeah. The longest we've done to date, I believe, is about 4.5 meters in-house. But yeah, I mean, they can. Another thing too is you can splice booms together. That's been done multiple times as well. So theoretically, it's as long as you need, as long as your application, as long as they can structurally handle it too, because there is a function of stiffness as you get farther away from the root. So, all right. Well, thank you.